Dear students, today I am going to discuss group theory. I will emphasize on the counting techniques in group theory, which will help you a lot in solving problems in competitive exams. Let us start. First of all, we will discuss some tools which will help you to solve the problems. First is Euler's phi function. The number of positive integers less than n, which are coprime to n, denoted by phi n, is called Euler phi function. So phi n is defined like this: cardinality of the set of natural numbers m such that m less than equal to n and greatest common divisor of m and n is equal to 1. We have some results. First is, if p is a prime, then phi of p is equal to p minus 1. Second, if p is a prime, k greater than 0, then phi of p raised to power k is equal to p raised to power k minus p raised to power k minus 1, which can be written as p raised to power k into 1 minus 1 by p. Third result is, if n greater than 1 has prime factorization, n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, p3 raised to power alpha 3, pk raised to power alpha k, then phi of n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, p3 raised to power alpha 3, up to pk raised to power alpha k into 1 minus 1 by p1 into 1 minus 1 by p2 up to 1 minus 1 by pk. Now, second tool is number of divisors, which is denoted by tau n. Given a positive integer n, let tau n denotes the number of positive divisors of n. We have a result. If n greater than 1 has prime factorization, then n is equal to p1 raised to power alpha 1, p2 raised to power alpha 2, p3 raised to power alpha 3, up to pk raised to power alpha k. Then tau n is equal to alpha 1 plus 1, alpha 2 plus 1, up to alpha k plus 1. Now, next tool is sum of the divisors, sigma n. Given a positive integer n, let sigma n denotes the sum of positive divisors of n. Now, what is group? A group is a set G with a binary operation G star G to G defined by G, G dash goes to G star G dash satisfying the following properties. First is existence of identity element, means there is an identity element denoted by E which satisfies the following property: G star E is equal to E star G is equal to G. Second property is existence of inverse. Every element G of G has an inverse denoted by G inverse. In other words, we can say this G must satisfy this property: G star G inverse is equal to G inverse star G is equal to identity. Third property is this binary operation star is associative. Associative means, in parenthesis, G1 star G2 star G3 is equal to G1 star bracket G2 star G3 for all G1, G2, G3 belongs to G. Now we have some examples. Number first, set of integers denoted by Z with respect to addition plus with respect to addition is a group. Similarly, Q and R and C. These Z, Q, R, C with respect to addition are groups. Number fifth is set of integers with respect to multiplication is not a group. Why not a group? Because here multiplicative inverse does not exist in set of integers. So this is not a group with respect to multiplication. Next example is set of rational numbers with respect to multiplication is not a group. Why not a group? Because here 0 don't have multiplicative inverse. Example number 7th is the set Zn is equal to 0, 1, 2, 3 up to n minus 1 for n greater than equal to 1 is a group under addition modulo n. What is addition modulo n? Means, suppose we will add two integers and we will divide by n, then the remainder must belong to this set. Now, for any j greater than 0 in Zn, the inverse of j is n minus j. This group is usually referred to as the group of integers modulo n. Now, what is abelian group? A group G is said to be abelian or commutative if A star B is equal to B star A for all A, B belongs to G. We have some examples. Z plus Q with respect to plus, R with respect to plus are abelian groups Second example is set of n cross n matrices with respect to addition forms an abelian group. Third example, set of all n cross n non-singular matrices with real entries denoted as GL and R forms a non-abelian group under matrix multiplication. This group is known as general linear group of degree n. Fourth example is Sn for n greater than equal to 3 is non-abelian. You are not familiar with this group, so we will discuss this group. Permutation. Let S be a non-empty set, then any mapping F from S to S, which is 1, 1 on 2 is called a permutation on the set S. In other words, permutation is a bijective mapping from the set S to itself. Now we have some examples. Let S is equal to 1, 2, 3. A map from S to S defined as Fi is equal to I for all I 1, 2, 3. We can say this is identity mapping. Second is a map G from S to S defined as G of 1 is equal to 2, G of 2 is equal to 3, G of 3 is equal to 1 is a permutation on the set S. Similarly, the third example is also an example of permutation on the set S. Now, here we have a remark. Let S be a non-empty finite set with cardinality n. The number of 1, 1 onto mapping from S to S is equal to n factorial. It means we can define n factorial number of permutations on the set S. Now, composition of permutations. If F and G are two permutations on a non-empty set S, then composition of permutations, that is F circle G and G circle F, are also permutations on the set. Why? Because composition of two bijections is again a bijection. So this F circle G and G circle F are also permutations on the set S. But here we can conclude that F circle G and G circle F are not equal in general. Let us see example. Here we have an example. Let S is equal to 1, 2, 3 and consider two permutations on the set S defined as follows. Here we have defined F and G, and clearly we can see here F circle G and G circle F are not equal. So you can see this. Now, what is symmetric group? Let S be a finite set, then Sn is equal to F such that F from S to S, F is 1, 1 and on 2 forms a group under the composition of mappings. This group is called symmetric group. Cardinality of Sn is equal to n factorial. Now, we have a notation. Suppose we have a group, symmetric group S5. Let us take a element of this group. Suppose sigma belongs to S5. We can use this notation. It means 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. Now, cycle decomposition we can write. Cycle decomposition of sigma is equal to, because 1 goes to 2, 1 goes to 2. So we will write 1, 2. Then 2 goes to 3. So we will write 3 next. Then 3 goes to 4. We will write 4. Then 4 goes to 5. We will write 5. And again 5 goes to 1. So we will close the bracket here. So sigma is a 5 cycle. Next example. That tau is equal to 1 goes to 1, 2 goes to 2, 3 goes to 4, 4 goes to 3, 5 goes to 5. So here we can write it 1 goes to 1. So enclose this in single bracket. Similarly 2. Now 3 goes to 4 and 4 goes to 3. We will close the bracket here. Now 5 goes to 5. So here 1, 2 and 5. This will behave like an identity element. So here we have a 2 cycle. 3, 4. So this is a 2 cycle. Now, even permutations and odd permutations. So first of all, we define even permutation. Let sigma belongs to Sn. We say sigma is an even permutation if the number of transpositions required to express sigma as a product is even. Here, transposition means a 2 cycle, cycle of length 2. Okay. Now, odd permutation. Let sigma belongs to Sn. We say sigma is an odd permutation if the number of transpositions required to express sigma as a product is odd. Now, we have a result. Order of a k cycle is a k. And transposition, we have discussed earlier. A 2 cycle is called a transposition. Now, we have a result. Every element sigma belongs to Sn can be written as a cycle or as a product of disjoint cycles. Now, alternating group. let Sn n greater than 1 be a symmetric group, then An is equal to sigma belongs to Sn such that sigma is even permutation forms a group of order n factorial by 2. Here, An is called the alternating group. An is a subgroup of Sn. Result, the number of distinct cycles of length k in Sn is n factorial upon k into n minus k factorial. We can see this example based on the result. Okay. Order of an element. If G be a group, then order of an element A belongs to G is the least positive integer R such that A raised to power R is equal to identity, where E is the identity element of G. If no such least positive integer exists for an element A belongs to G, then we say that A has an infinite order. Here we can write order of OA to denote order of an element A. We have some results. If A belongs to G, then order of A is equal to 1 if and only if A is equal to identity. Means identity element is the only element in the group which has order 1. Now, second result is if G is a finite group and A belongs to G, then order of A can never exceed the order of G. Third result is if sigma belongs to Sn, has a cycle decomposition. Sigma is equal to sigma 1, sigma 2, sigma 3 up to sigma k, and sigma is a mi cycle, and these cycles are disjoint. Disjoint means there is no common element. Then order sigma is equal to LCM of m1, m2, m3 up to mk. So here we have a very good example. In this result number 3, these disjoint cycles plays a very important role in this result. This result may not be true if we don't have disjoint cycles. So this concept we have elaborated in this example. Sigma is equal to 1, 2 into 1, 2, 3. So here, if we will do product of these permutations, then we will get the answer 2, 3. So sigma is a 2 cycle here. It is also a product of 2 cycle and 3 cycle. But order of sigma is equal to 2 because it is a 2 cycle. But LCM of 2 and 3 is equal to 6. But 6 is not equal to 2. So here above result does not apply because 1, 2, permutation 1, 2 and permutation 1, 2, 3 are not disjoint cycles. Now, subgroup. Let G be a group. A subgroup H of G is a subset of G which has the following properties. First, H is closed under the binary operation of G. Means if A, B belongs to H implies A into B belongs to H. Second property, E belongs to H. Third property, if A belongs to H, then A inverse belongs to H. We have a counting technique here. Number of subgroups of Zn is tau n. We can calculate tau n easily. Here we have a problem. Find number of subgroups of a cyclic group Z6. Number of subgroups of a cyclic group Z6 is equal to tau 6. We can calculate easily. First of all, we will write the prime factorization of 6, which is 2 raised to power 1 into 3 raised to power 1. So how to calculate tau? We will add 1 in powers. So 1 plus 1 into 1 plus 1 is equal to 4. Now, what is cyclic group? Let G be a group and let A belongs to G. The subgroup generated by A is the subgroup A raised to power n. N belongs to Z is equal to, this is the notation to denote the cyclic group generated by A. Here A is called the generator of the group. Here we have some results. If D is a positive divisor of n, then the number of elements of order D in a cyclic group of order n is equal to phi D. Number 2, let G be a group of finite order, then G is a cyclic group if and only if G has at least one element whose order equals to the order of the group. Third result is every cyclic group is abelian. Fourth is number of generators of a cyclic group G of order n is phi n. We can see one example based on this result. Number of generators of cyclic group of order 27 is phi of 3 raised to power 3 is equal to 3 raised to power 3 minus 3 raised to power 3 minus 1 is equal to 27 minus 9 is equal to 18. Next result is every group of prime order is cyclic. Next is number of subgroups of a cyclic group of order 12 is tau 12 is equal to 6. Now, here we have a question. Is abelian group cyclic? Answer is no. Why? Suppose we have a group G defined as E, A1, A2, A3. This A1 identity is always of order 1. Here A1, A2, A3 are of order 2. We have defined a structure here. So this group is called Klein-4 group. G is called Klein-4 group. Now the question is it cyclic? Answer is no. Why? It is not cyclic because it has no element of order 4. We are using here result number 2. Now I have written an example. This example is also a Klein-4 group because it satisfies the all properties of the Klein-4 group. Now, center of a group ZG is equal to A belongs to G such that AX is equal to XA for all X in G. We have a result. Suppose G is a abelian group, then ZG will be the whole group G. Now, center of a group is a subgroup of G. We have a result. If cardinality of G is equal to P raised to power N, where P is a prime, then cardinality of ZG is greater than 1. Homomorphism. A homomorphism of groups is a function phi from G to G dash such that phi of AB is equal to phi of A, phi of B for all AB belongs to G. Here G and G dash are groups. Suppose we have an example, phi from Z to Z. Fix an integer n. Phi A is equal to NA. NA can be written as A plus A up to n times is a homomorphism. Clearly, we can check here. An operation is addition because we know Z is a group with respect to addition, not with respect to multiplication. So now we have a counting technique again here. The number of group homomorphisms from Zm to Zn is GCD of M and N. So based on the result, we have example. The number of group homomorphisms from Z2 to Z3 is greatest common divisor of 2 and 3 is equal to 1. Now, isomorphic groups. Two groups G and G dash are isomorphic groups, or we can say that they are isomorphic to each other if there is at least one mapping from G to G dash, which is isomorphism, means homomorphism 1, 1 and on 2. Some examples, Z4 and K4 are not isomorphic. Why not isomorphic? Because Z4 is a cyclic group, K4 is not cyclic group. Second example is S3 and Z6 are not isomorphic because S3 is non-abelian and Z6 is abelian. Rather, we can say Z6 is cyclic. Number 3 example, any infinite cyclic group is isomorphic to Z. Fourth is, any finite cyclic group of order n is isomorphic to Zn. Now we have a result. Let G be an abelian group of order n is equal to P1 raised to power alpha 1, P2 raised to power alpha 2, P3 raised to power alpha 3 up to Pk raised to power alpha k, prime factorization of n. Then number of abelian groups of order n up to isomorphism is equal to P of alpha 1 into P alpha 2, P alpha 3, P alpha k, where P alpha denotes the number of partitions of alpha I. Here we have a problem. The number of non-isomorphic abelian groups of order, this is fill in the blank. How can we calculate? We will find partitions of power, means partition of 2, partitions of 3, partition of 4. So partition of 2 is equal to 2, partition of 3 are 3, partition 4 are 5. So we will multiply 2 into 3 into 5. So we will get the answer 30. Now, suppose we have a homomorphism phi from G to G dash such that phi of AB is equal to phi of A into phi of B for all AB belongs to G. Here, kernel of phi is equal to A belongs to G, phi A is equal to EG dash, identity of G dash. Image of phi is equal to phi of A belongs to G. Kernel phi is a subgroup of G and image phi is a subgroup of G dash. Now, normal subgroups. Let G be a group. A normal subgroup H of G is a subgroup satisfying the property given G belongs to G and H belongs to H, G inverse belongs to H. Kernel phi and ZG are normal subgroups. Now, cosets. If H is a subgroup of a group G, the left coset of H are subsets AH, A belongs to G. Right coset of H are subsets HA, A belongs to G. Here we have another definition, index of a subgroup. The number of left cosets of H in G is called the index of H in G. It is denoted by this symbol. So next, Lagrange theorem. Let G be a finite group and H be its subgroup of G, then the order of H divides the order of G. Written differently, cardinality of H divides cardinality of G. Cauchy theorem. Let G be a finite abelian group. Suppose that a prime number P divides the order of G, that G has an element of order P. Now we have a result. Suppose G has order P or P square. Then the group G is abelian. Here we have an example based on this result. A group of order 9, we can write is 3 raised to power 2 is abelian. Now Syloh's theorem, very important theorems in group theory. So first of all, we will define what is Syloh P subgroup. Let G be a finite group. Let P be a prime number. Say cardinality of G is equal to N. We can write cardinality of G is equal to N is equal to P into P raised to power E into M, where E greater than equal to 1, M greater than equal to 1. P and M are co-prime. This means P does not divide M. Then Syloh P subgroup of G is a subgroup of order P raised to power E. Now, first Syloh theorem. Let G be a finite group of order N. Let P be a prime number such that P divides N. Write cardinality of G is equal to N is equal to P raised to power E into M, where E greater than 0 and P does not divide M. Then G has a Syloh P subgroup. Second Syloh theorem. Let G be a finite group and let P be a prime that divides cardinality of G. Then two Syloh P subgroups are conjugate. Here we have given the definition of conjugate subgroups. H and K are two subgroups of G. These will be, we will say these are conjugate if H equal to G, K, G inverse. Third Syloh theorem is, let G be a finite group and let P be a prime that divides cardinality of G. Here cardinality of G is equal to N is equal to P raised to power E into M, where P does not divide M. Let S be the number of Syloh P subgroups of G, then S divides M, and S is equal to AP plus 1 for some A greater than equal to 1. Here S is small. Example, let G equal to S3, cardinality of G is equal to 6 is equal to 2 into 3. S2 is equal to the number of Syloh 2 subgroups. S3 is denoted by number of Syloh 3 subgroups. Third Syloh theorem implies S2 divides 3 and S2 is equal to 1 plus 2A. So the only possibilities of S2 are 1 or 3. Again, third Syloh theorem implies S3 divides 2 and S3 is equal to 1 plus 3A. So only possibility is S3 is equal to 1. So G is equal to S3. Then if G equal to S3, then S2 is equal to 3. If G equal to Z6, then S2 is equal to 1. Here we have a result. Let P and Q be primes such that P less than Q. Let G be a group of order P into Q. Then G has a normal subgroup of order Q. By using above result, we can say that a group of order 6 has a normal subgroup of order 3. So here we have some references. First one is NPTEL course, Introduction to Abstract Group Theory by Professor Krishna Hanumantu, a very renowned mathematician. Second is Contemporary Abstract Algebra by Joseph A. Gallian. This is a very important book. And third one is Modern Algebra by A.P. Singh, Info Study Publications. This is again a very important book for competitive exams. So if you want to prepare for competitive exams, this book will help you a lot. So thank you so much, students. Thank you so much.